right. Hello, everyone, and welcome back to Comp 3430 Operating Systems. It is spring break this week for primary and secondary schools, and my partner is a middle school teacher, and my children are in primary school, and so that means that they're all on spring break this week, and I'm here with all of you, and I love being here with all of you. Yeah, so yeah, next week is the last week. Today is the last, the second last Monday, but the start of the last full week. Yeah. But yeah, they're going to be sending me pictures of stuff they're doing all week, and I'm just going to be sitting in my office and jealous of that. So this week and today, by the end of today's lecture, what I want you to be able to do is the two continuing things that we started last week. And as I said, these are just going to keep showing up. I might stop saying this in the beginning of every class, but I figured we're at the start of a new week, so I might as well bring it back up again that yes, today I want you to be able to continue to be able to explain how a process's entire address space can be provided or supported via the concept of virtual memory. And I want you to continue to be able to describe how the operating system works with the underlying hardware to manage virtual memory. Last week, we were looking at this idea of how do we take an entire address space and cram it into physical memory from the perspective of, let's just make these virtual address spaces much smaller than physical memory so that they can fit into physical memory. And this week, we're going to be moving on to a different approach, which is we're going to let the virtual address spaces stay extremely large, and we're going to fit them into virtual memory by doing something, into physical memory, sorry, by doing something just a little bit different in terms of the way that we're managing things. And that is, I want you to be able to begin to discuss the benefits of partitioning memory and address spaces. We've actually kind of already started to introduce this idea of partitioning physical memory. That's effectively what we were doing with base and bounds. Is I want to take my physical memory and break that into smaller pieces and then stuff entire virtual address spaces into those smaller pieces. And today we're going to be spending time, and this week we're going to be spending time thinking about this in the perspective of partitioning address spaces as opposed to partitioning physical memory. And the other thing I want you to be able to begin to do today is to compare and contrast methods for address translation. So again, I emphatically do not care if you can translate addresses. I really very much don't care if you can go through the mechanical process of translating a virtual address to a physical address. I believe that's irrelevant in the context of an operating systems course. It becomes relevant when you're thinking about hardware and when you're in something like Comp 3370 where you're thinking about computer organization, but from our perspective, from the operating system perspective, we sort of need to see the big picture and the abstraction of what's going on here, but I don't really care much about the actual mechanical act of translating virtual addresses into physical addresses. But that said, we should be able to begin to compare these two different approaches for doing virtual memory. So we're going to be looking at segmentation this week, and I want to be able to start making comparisons between segmentation and base and bounds from the operating system's perspective. So what kinds of things are the same across these two approaches? What kinds of things are different? How do we need to change our structures internally to better represent the idea of what segmentation is with address translation in terms of supporting virtual memory for processes? So last week, the bulk of our time was spent taking a look at virtual address spaces. And the purpose of this really was to give us all a common ground for being able to confidently say that the way that we have been told that address spaces work is actually the truth. This is really a thing when I run a program on a computer that has, I don't know, the typical computer that we've got. The virtual address space layout matches what we've been told so far. So we know for a fact that there's a program code segment that lives closer to the top of memory There's a heap that lives beneath that somewhere, and there's a stack that lives somewhere very close to the bottom of the virtual address space that we've got. We were able to observe this in two different ways last week. One, by running a program, so experimentally checking to see, like, does the code section, does the address of the main function live somewhere closer to the top of memory, and does a stack allocated variable live somewhere closer to the bottom of memory? And we saw that that was the case, or at least we were able to see that relative to each other, these addresses match this layout. And then we looked at the operating system's perspective. So we took a look at what the Linux kernel shows us about the address space layout for a specific process. And we were able to see things like in that maps file, the program's code is mapped into this virtual address space in a bunch of different places where they have different permissions. And then there's this part that's labeled the heap, and then at the very bottom, there's this part that's labeled as the stack in this address space. And so we were able to confirm that, yeah, for sure, the address space layout that we were expecting is actually the case in the processes that we were running. This idea of taking these virtual address spaces and sticking them into physical memory is kind of a problem, because the addresses that we were looking at in the sample, the process that we were running, they were quite a lot bigger than the physical memory that I have on my actual physical system. And so the first idea that we have with supporting virtual memory here is to take this idea of an address space and just make it smaller than physical memory so that we can put the entire address space into physical memory somewhere. The main constraint that we have with all of these different virtual memory systems is that the layout of the virtual address space has to remain approximately the same as what we had when we're told about it and when we're thinking about it. And that's kind of like a little bit weird, honestly. Like, why does it have to remain the same? Why do all these processes have to have the same address space layout as what it was like when they were running entirely by themselves with no operating system underneath? The address space layout that we're talking about right now, code and then heap and then stack, this is coming from a time where we had machines that would run one single program at a time. And there were, like, the operating system was literally the person that would spool up the tape that gets put onto the machine that runs the program. Why does it have to remain the same? And this is really kind of, and you can not quote me on this at all, but, like, I'm sure that someone somewhere effectively said, it's going to be too hard to change all 300 programs that are in existence right now. And so we have to live with this design forever. And now that we've gotten to the point where we're at right now, it's impossible to change it because we've got countless numbers of programs that rely on this. So all the virtual memory stuff that we're doing, all the way up to right now, literally running on my laptop here and literally running on all of your laptops, it fits into this virtual address space, even if it doesn't actually look like that in physical memory. And it doesn't look anything like that in physical memory. But someone somewhere in 1973 probably said, it's just going to be too hard to change all these things. Let's start today by doing a little bit of a quiz about virtual memory in general, and then moving on to looking at base and bounds. I'm going to hold this up here for about 10 seconds, and then I'm going to pop over to my Mentimeter slides. Okay, I'm going to switch over to Mentimeter. The code should stay up at the top of the screen. And I'll verbally confirm with you in the room that you are able to connect to this today. Okay, awesome. I'll give you about 10 more seconds. All right, so we got 4 questions in this quiz. The first 2 are going to be kind of review of VM in general, and then the next 2 are going to be about base and bounds specifically. And then there are going to be some additional slides in this presentation that we're going to come back to later. So I'll bring this back up, but if you can stay connected, please stay connected after the quiz is over. All right. Okay. Yeah. So this is the same this is the same questions that I asked last week, and I wanted to ask it again to make sure that we're on the same page about this. And I'm really happy to see that we are now skewing much more towards the responsibilities that an actual operating system would have in the context of supporting virtual memory. So an OS has the responsibility to have some additional information in the process control block. In the task struct that we have in our Linux kernel, there's got to be something in there that describes what this process's virtual address space looks like. We have to have something in the process control block for our OS to be able to do context switching appropriately. Keeping track of free space in memory. In terms of what we were looking at so far with base and bounds, this is really just, has this segment of physical memory been used by a process or not? We could do that going all the way back to file systems. We could do this with an allocation structure. We could use a bitmap to say that this block has been allocated or it has not been allocated. And that's awesome. That's actually really great because it makes it really easy for our OS to keep track of which thing has been allocated and which has not been allocated because we have this bitmap structure. Converting the actual virtual addresses to physical addresses, again, our OS cannot do this fast enough. It's conceivable. It is conceivable for an operating system to have the responsibility of actually doing this translation. It's possible for that to happen, but it's so intensely slow because for every single instruction that would need to be executed in this code's address space, we'd have to do a translation. We'd have to do a translation to get the instruction, and then we'd have to do a translation on the instruction's data and the things that it has within it. And then we'd have to do translations for like where it's supposed to put its data back in memory. And then we'd have to do another translation on the program counter. So to do one instruction execution, we'd have to do 4 or 5 or more different translations to be able to accomplish this. And so the OS just cannot do this fast enough. It is not possible for the OS to do this fast enough. If you are in a situation where you are implementing a system emulator, if you are building a system emulator, yes, you have to do this. But in terms of actually running an OS on an actual machine, it's too slow. Even with the fastest possible processor, it is too slow to be able to do these translations. The last part, checking if a process uses unallocated memory. Again, our OS is responsible for handling that situation, but it is not responsible for checking to see if it is an invalid access. Our OS doesn't know that you've caused a segmentation fault, but it sure knows what to do when it's told that a segmentation fault has happened with your code. All right, here is the next question. And I'm just going to press enter on this, and I'll ask it right away. Yeah, okay, awesome, good, yes. Having additional registers. That's, again, like last week, it's kind of a weird thing to say as a responsibility, but what I ultimately mean by this is there's got to be something that the hardware can be configured to do the translations for that process that's currently running. The OS has to put this information somewhere for it to be able to do that. Keeping track of the exception handlers, and again, this is importantly different than handling memory access exceptions. The semantics here are the hardware knows who to call and who to tell, so what address to start executing at when this happens, but it doesn't know what a process is. So it can't kill our process, for example. It's not possible for this thing to handle the exception. It's really just able to tell the OS, this happened, do something about it, please, because I can't do anything. I don't know what a process is. Keeping track of free space here. Again, this idea is possible in memory in terms of if we had a fixed size of physical memory, in perpetuity, we could do this, but in terms of practical supporting the keeping track of what is and what is not allocated, it's not really possible for our hardware to do this. This is something that our operating system has to do. All right, so awesome, yes. All right, ET's at the top here. I now suddenly cannot remember if this was something that happened in this class or some other class. Was it this class? Okay, yeah. And it's Sweden, right? I think it's Sweden. I think it's Sweden that flag is. Okay. Yeah, okay, it is Sweden, okay. Okay, we got 2 more questions, and these ones now are moving on to base and bounds here. Okay, all right, okay. So with base and bounds, we are segmenting something. I want to give you some credit for selecting this one. I want to give you credit for this because we are indeed segmenting something related to memory. We are definitely segmenting something related to memory here. The thing that we're segmenting in the case of base and bounds is physical memory itself. The entire idea here is that we're going to take these virtual address spaces and squish them down so that they are now smaller than physical memory. So if I've got 32 gigs of RAM in my laptop, I've got 32 gigabytes of physical memory. The idea of base and bounds is that I'm going to say every process gets some fraction of physical memory. It gets 4 gigabytes of physical memory. It's got that as an entire address space. I'll come to you in just a second. It has that much as an address space, and I'm just going to plop the whole address space into physical memory here. I'm not breaking my virtual address space up at all in this case. In base and bounds, I'm just sticking the entire address space into that location in memory and chucking it in there. Segmenting processes into tiny pieces, they're related. They are certainly related, but the main idea here is that we're breaking up our physical memory into tiny pieces so that we can fit entire virtual address spaces into it. Yeah?
I just wanted to ask, does that how VMs technically work when you allocate some memory to them?
How a virtual machine might work? That's a complicated question. Virtual machines, there's many different kinds of virtual machines that we could be having support for.
Not necessarily lightweight container, more like big VMs.
Even within that, so it's possible for us to be running something called a hypervisor that would be sitting where our operating system would normally live. And then that hypervisor could potentially say, yes, you have direct access to this specific physical memory. But then internally, the operating system would still be doing stuff like the process's address space is within that. So if you want to think about it from that perspective a little bit, yes. But one of the other major differences between that idea and what we're thinking about here is that when we're segmenting our physical memory up, we're segmenting it into fixed size spaces where our hypervisor might be able to say things like, you get a gigabyte and you get 10 gigabytes, and you get 500 megabytes and you get 32 gigabytes. And it's not necessarily separating it all out into the same fixed size chunks.
Are we technically allocating the actual physical memory in when we actually tell VMs to have this much, or are we actually just virtualizing it?
I don't know that I can competently answer that question because I don't really know that much about how virtual machines are implemented. But again, there's the idea of this hypervisor that lives where our operating system lives, and then there's ideas like VMware, for example, where this is an application that's running within your host operating system. And the host operating system might be giving it direct physical access to memory, but I'm really not sure. Yeah. Yeah, I'm sorry I can't answer that any more confidently. Yeah,
I was just curious.
yeah. Okay, so the main idea here is that we're segmenting our virtual address, we're segmenting our physical memory into fixed size chunks here, and the entire virtual address space gets stuck into that fixed size chunk. Here is our last question. Yeah, okay, awesome. I want to give this one so much credit. I know I'm marking it wrong here, but I really, really want to give you credit for this. Yeah, this is absolutely still a problem. But I want to put some context into why I put a red X here. The context that I want to put into why I put a red X here is that I looked this up yesterday. I looked this up because I needed to know. I looked this up. You can buy from Dell a server that has 16 terabytes of physical memory in it. Yeah, huh? That is mind-blowing. That is insane. That is like, I don't, 16 terabytes is so much physical memory. Like, I am not that, I'm not that old. Like, people that were around in the 80s worked with computers that had like 64 kilobytes of memory. And so even a gigabyte is some mind-boggling size of number.
I remember when 8 gigabytes was like the stuff.
You remember when 8 gigabytes was the stuff. I remember when 1 gigabyte was the stuff. Like, that's where I'm at. And so for 16 terabytes of physical memory to be available in an actual system, it is prohibitively expensive. We're talking $500,000 at least for a server that's like this.
Imagine keeping it cool.
Imagine keeping it cool. But with 16 terabytes of physical memory, you could actually reasonably give hundreds or thousands of processes 8 gigabytes each. You could very reasonably do that. And MacBooks are still selling with 8 gigabytes of physical memory. And so it suddenly becomes feasible to do fixed size virtual address spaces and just break physical memory into these smaller chunks and just say, Chrome, you get 8 gigs. There you go. Use it. Do whatever you want with it. Yeah, I really want to give you credit for this, and I am spiritually giving you credit for this. Like, please, yes, you picked the right thing, but I've changed my answer on this, and that is that this is maybe less of a problem as memory sizes become much, much bigger. But this is still a huge problem. Internal fragmentation. I'll come to you in just a second. Yeah, if I can buy 16 terabytes of physical memory and I can give every process 8 gigabytes of RAM, I can give it its entire 8 gigabyte virtual address space, and you can just do what you want with it. Chrome might actually use all 8 gigs, but my terminal is not going to use anywhere near 8 gigabytes. And it's going to be allocated to that terminal, and it's going to use hardly anything. It's going to use next to nothing in terms of the actual address space that it's been giving. And so while we might be able to do that, we're still going to be wasting so much space that has been allocated to my terminal, but then never actually used by my terminal. Yeah.
But I think the fixed size problem is also like it has the underlying problem of internal fragmentation. Like that's the main problem that's there as well.
The main problem really is internal fragmentation, but even if we didn't fix the sizes, you're right. The problem is just allocating it, period, that we've over allocated, and then the thing that's actually using it is not actually able to use it. Internal fragmentation and fixed size segments are related to each other. Yes, they're definitely related to each other, but we could have internal fragmentation without fixed size chunks. Yeah. Yes. Okay. See where we were at the end here. All right, so ET got kicked out and Room got to go up at the top. So congratulations to whoever Room was. Like I said, I'm going to put some more questions in here. They're not quiz questions, though. It's more of a I want to get feedback from you style questions. So if you're able to stay connected to this, great. But you should hopefully be able to rejoin when we get to the point of having that part of our lecture. Are there any questions about anything before I move on? We're all okay? Okay, awesome. All right. The main problem that we've got with base and bounds is internal fragmentation. We are allocating these big chunks of address spaces for these processes that we're running, but we've got a bunch of space that's allocated within there and is not really actually being used between the heap and the stack. And I'm kind of hand-waving here in terms of the abstract idea of between the heap and the stack. There might be other places where we're not really actually allocating things. Like if we have space between our code segment and our heap, there might be some space in between there that's not actually being used by anything, but it's been allocated to a process. And so the solution to this, in terms of what we're looking at this week, is, well, just don't allocate that part. If you're not ever going to use it, just don't allocate it in the first place. And that's kind of baffling. Like, if we've got these address spaces that are fixed in size, how am I supposed to put this chunk of memory into physical memory but not allocate the middle part? Because nothing's really going to fit in there. The problem that we've got, or the idea that we have with this internal fragmentation, is that if we were to take all of those middle parts and add them up, we might be able to put more stuff in there. But the middle parts are still not really quite big enough to fit everything. And so our overall solution is going to be, rather than allocating the entire virtual address space into physical memory, let's just allocate parts of the address space in physical memory. And the parts that we're going to allocate are the parts that we are actually using in the process. And these are going to be our segments in the process. The other half of this is going to be that we're not going to fix the size of the segments. So with base and bounds, what we were saying is, I'm going to break physical memory up into some fractional size of itself. I'm going to have these partitions that are each fixed in the exact same size, and I'm going to stuff an entire virtual address space inside of that fixed partition. With segmentation, what I'm saying is, I'm going to take my virtual address space, I'm going to take the parts that I'm actually using, and I'm not fixing the size of them. So they're going to be variable in size as opposed to fixed in size. Let's visualize this idea. So I'm going to pop over here to my tablet. And what I've got is that we've got this idea of base and bounds here on the left side of our screen. And this is physical memory for me. I'm going to take some stuff away from this, from what I had last week, and I'm going to say here that the operating system's got to live in physical memory somewhere. It has to be there. And so we're going to say that it gets the first partition that we have in base and bounds. After that, we're going to allocate an entire address space into one of these 4 slots that we've got here. This is PID 1 that we've got running here, and we're just going to hand wave and say that this is my web browser, this is Firefox, and we've got this entire address space, and we're just going to jam it inside of that one slot. When another process starts, I'm going to be putting it into the next slot, but I'm going to put its entire address space into that. And when a third process starts, I'm going to jam it entirely into that third slot that we've got in this physical memory that has been partitioned. One thing I want to note about these partitions that we've got in this virtual address space is that the addresses, the physical addresses in each of these are being used to help us do the partitioning. The first 2 bits of every address in this partition of physical memory starts with 00. every address in this part starts with 0, 0. Every address in the partition that I've allocated for Firefox starts with 0, 1 in binary. So we're talking about binary here. It starts as 0, 1 in binary. Every address for the partition that I haven't yet allocated here starts with 1, 0. And every address in the remaining partition that I have not yet allocated all start with 1, 1. And so we are able to use our addresses to do this partitioning. So these are physical addresses that we're using to do the partitioning, and we're able to make decisions about that. Again, emphatically, I do not care if you can translate addresses, but the idea of using the addresses for segmentation of physical memory here is an important concept that isn't really directly translating them, but gives us the ability to say, yes, these physical addresses live in this location or this partition of physical memory. So we've got this virtual address space layout here, right beside our physical memory. And we've got our code section, and we've got our heap, and we've got our stack. The problem that we are really identifying with base and bounds here is that when we allocated this entire thing, we were in a state where we've got this section that's in between our heap and our stack that has been allocated, but it hasn't actually been used by anything. And so this is our idea of internal fragmentation, but it kind of gets worse. It gets worse in the sense that a lot of applications aren't even going to use the entire part of the code segment that they've been allocated here. So if I've got a code segment like this, and I've got a heap that looks like this in terms of stuff that has actually been allocated, I've got a stack at the very bottom that's been allocated here. And so these are things that are actually allocated by the process that we're working with. If we were to take this and actually put that into the physical memory, into the partition that we've got for each of these processes in base and bound, it's not just that part in the middle that has been allocated but is not used, but now we've also got these giant chunks that are going to be allocated and not used. And so the main idea with segmentation here is that rather than having a virtual address space that starts at 0 and goes up to some fixed size for fitting into physical memory partitions, we're going to have a virtual address space here that still starts at 0, but it's going to go all the way up to 64 bits of gigabytes here. So whatever number of exabytes that actually happens to be, some huge amount of space that we're going to allocate to this virtual address space. Once we've got that, we're still going to have physical memory in terms of what we've got in our machine. This is still a pretty hard limit. There is a website that's called downloadmoreram.com, but doesn't actually put anything in your machine. We can't make our physical memory bigger than what we've got. And so I don't think it does anything. Even with this setup, we're still going to have a physical memory space that is limited to, let's say here, 32 gigabytes. And we're still going to need to have our operating system living somewhere here. And for our discussion, I'm going to put my OS up here, up at the top. But I importantly want to note that it doesn't take an entire partition. When I'm drawing these two physical memories on either side, I'm trying to draw them to scale relative to each other. With base and bounds, we had to allocate all addresses in the physical memory that started with 00 to our operating system, and that was 8 entire gigabytes. Over here, we're not allocating an entire partition of physical memory to our operating system. we're going to say that this is, I'm just going to hand wave here, and I'm going to say that this is 5 gigabytes instead of 8 gigabytes. We've allocated 5 gigabytes for our operating system here. This is where our operating system will have its own code. This is where the operating system will have things like its thread control blocks and process control blocks for all the structures that it has running in the system right now. With segmentation, what we are then going to do is we're going to allocate the segments that are used and actually used by the process by partitioning my virtual address space. So where I had been partitioning my physical address space over here with base and bounds, I'm now going to be partitioning my virtual address space. And I'm actually going to partition it in the same way. I'm going to partition it in the same way. And so what I'm going to say is that in this partition of my virtual address space, these addresses all start with 2 zeros in binary. These addresses all start with 0 and 1 in binary. These addresses all start with 1 and 0, and these addresses all start with 1 and 1. So I've partitioned my virtual address space into 4 different partitions. I'm going to take my partitions that I've got here, and I'm going to allocate only that in the virtual partition that has actually been used by the process. So when I start this process up, when I start up Firefox, I'm going to take the part of the code segment that has actually been used, and I'm going to stuff it somewhere into physical memory. I'm going to make arbitrary decisions right now about where I'm putting this, but this is where our free space management policies come into play. When we're thinking about where to stuff things, it's kind of like hand waving the task that gets to go next is just this random chaotic thing, and now we see that there are scheduling policies that make this decision. For now, I'm just going to say I'm going to put these anywhere that feels like the right spot. But we're going to actually use free space management policies to actually make this decision about where things go. But I'm going to say things like, this is the code section for process 1. And I'm going to allocate in physical memory just this one little slot of blocks that I have in my graph paper here. My heap is going to start at the addresses that start with 0, 1 in my virtual address space. And I'm going to just stick this into physical memory somewhere where there happens to be 2 spaces free. And finally, I'm going to take my stack and I'm going to stick it into physical memory somewhere where there's enough space for this one part of my virtual address space that I happen to currently be using. And so now the setup that we've got is that we're with base and bounds, process ID 1, which was Firefox, had a virtual address space that was 8 gigabytes in size, and we stuffed the entire thing into our physical memory here. Now I've got this virtual address space that is effectively unlimited in size. 64 bits is so mind-bogglingly big, and in 50 years, we'll all be looking back and saying, ha, that's ridiculous. But for now, it's so unimaginably big that we've got a huge amount of space that could potentially be used by this process. It's no longer limited by just 8 gigabytes. And instead of allocating the entire virtual address space, we are only allocating the parts of the address space that we are actually currently using, and we're allowing these allocations that we're making for this process to vary in size. That means some interesting things like what I've done here, which is that in physical memory, the code and the stack and the heap can be completely different locations relative to each other. But when we, the operating system, are configuring our hardware to do address translations, the hardware is going to map those back into the physical address, to the virtual address space that we've got for this process. Now, this really importantly leaves a huge chunk of free space into which we can put other processes. And so now we're not limited to just having 3 processes in this system. We can have as many processes as we can fit into physical memory once we've accounted for all the allocations that these different processes are using. We've defeated internal fragmentation. Congratulations, everybody, we did it. We've defeated internal fragmentation. And we've backed ourselves into a different corner instead of with internal fragmentation. But we will get to that when we get to it. So I'm going to leave this up here for a second. And I want to emphasize here, we are no longer allocating entire virtual address spaces. We're no longer allocating entire virtual address spaces. We're just allocating the parts of the address space that we are actually using for the process. And we're putting those actual allocations into physical memory. The sizes of these can change. So I can have a bigger heap than I have a stack. I can have a bigger code section than I have a heap. I could have a bigger stack than I have code and heap sections. I can have bigger parts or smaller parts. They vary in size. And I've got a bunch of extra free space that I otherwise did not have access to. With base and bounds, in our process control block, we had to have at least one additional value for our context, which said that this is the start in physical memory of this virtual address space. System-wide, we might have said all address spaces are this size. We may have also put that information into the process control block for a process. But with base and bounds, we had to have at least one of those things. I'm going to go back to my Mentimeter slides now. And the first question that I want to ask you, I'm going to come back here first, actually. The first question that I want to ask you in terms of comparing with base and bounds is going to be, what's similar between these two things? And I want us to be able to think about that in terms of just like overall structural similarity, but I also want us to be able to think about that in terms of the kinds of things that we as an operating system might need to have to be able to do this. How does segmentation fix the problems that we've got in base and bounds? We'll ask these in step, so you don't need to answer them all right now. And what do we need to change about the OS to support segmentation compared to what we were doing with base and bounds? So I'm going to pop back to the Mentimeter slides now. And the first question that we've got is, how is segmentation similar to base and bounds? So address translation, yeah, 100%. We are doing address translation in both of these. So in terms of basic superficial similarities, yes, absolutely, we're doing address translation between both of them. I'm going to pick on this one, and I'm going to say that, yeah, they both break down memory, but I want to strongly emphasize that with base and bounds, we're partitioning physical memory. And with segments here, what we're doing is partitioning our virtual address space. We're doing partitioning in both of those cases, though. We are 100% breaking down some form of memory, whether it be virtual or physical, but we're doing it in both of those things. Both need registers. Yeah, both need hardware registers, so we must have some kind of hardware support. We still have different segments and use a virtual address space. So yeah, we still have those same named segments that we had in the virtual address space that we were loading up with base and bounds. How does segmentation fix the problems that we had with base and bounds? And there were two problems that we had with base and bounds. One was that we had fixed sized address spaces, and that led to things like we can only have this many processes running ever in the system, and the other was internal fragmentation. So yeah, it gets rid of allocated but not used space. Doesn't over allocate. It reduces the internal fragmentation, only allocating space for what's needed. So all of these together mean approximately the same thing to me. Of these answers, the best one to me is going to be these two right here. So getting rid of allocated and not used space and only allocating space for what's needed. When I'm thinking about questions like this and I look at these answers, these two are the best ones because they tell me exactly what the solution is to this problem. Internal fragmentation definitely was a problem, and I want to give credit for that. But these two actually explain what the problem is with internal fragmentation. How many processes can we run with segmentation compared to what we were able to run with base and bounds? I hope I configured this so that you can answer multiple times. More. Good. Yeah. Okay. Yes. More. Yes. I like that answer very, very well. Yes. We can definitely run more processes. We had a fixed number of processes when we had a fixed number of partitions for our physical memory. And now we have infinite within the bounds of how much memory we actually have. So how much memory we're actually able to allocate, we have infinite up to that point. So yes, okay, good. What do we have to change in terms of our operating system to be able to support the change that we've made with segmentation compared to what we had with base and bounds? With base and bounds, we had to have at least a register, at least a value in our PCB to support which segment or which partition we're getting our stuff put into. How does it have to change with segmentation? We could have access to the whole address space to store anywhere. Yeah, we gotta have registers for every segment in every process. Base and bounds for, yes, excellent. So we've got to basically have a base and a bound for every single segment that we're allocating for this process. And because we are allowing flexible sizes for our address allocations of our address space, my code might be differently sized than my heap. I have to have a bounds. With base and bounds, we're able to hand wave and say, they're all the same size, so maybe you just have this in one global system level thing. Every allocation might have a different size with segmentation, and so we have to keep track of how much has actually been allocated by that process right now. Data structure to keep track of. Yeah, so basically keeping track of the allocation that we've made. Okay, awesome, yes. All right, so the big things that we've got here is that segmentation is similar to base and bounds. We're doing partitioning in both cases. The partitions that we're talking about are going to be different from, the partitions that we're talking about in base and bounds are of our physical memory, and the partitions that we're talking about with segmentation are our virtual address spaces. Segmentation fixes the problems that we've got with base and bounds in the sense that we no longer have this internal fragmentation problem. We do a little bit. Like, we're going to have to over allocate the heap a bit so that our process isn't constantly asking for it to be bigger, but we no longer have this massive chunk in the middle of our address space that has been allocated to a process, but it's no longer used. And in terms of what we have to do as an operating system, we're going to have to add base and bounds registers for every segment that we've got from this virtual address space. This might be that we have 2 segments. It might be that we have 4 segments. Depending on how many segments we want to have dictates how many values we need to add to our process control block to be able to support that. All right, so thank you all for participating in that. At this point, you should be able to continue to be able to describe the idea of virtual memory and how it's supported by hardware. And you should now be beginning to be able to discuss the benefits of partitioning memory, so base and bounds, and address spaces, segmentation. And you should beginning to be able to compare and contrast these methods. So we're going to continue on with this when we get to paging. But for now, you're able to start making comparisons between segmentation and base and bounds for virtual address translation. That's it for today. Thank you all for coming out. I hope that you have a great rest of your day, and I will see you on Wednesday, where we will be taking a wild ride through segmentation fault. Bye, everyone.